Recording in progress. 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 Recording in progress.
So, very good morning and most welcome, Dr. Stevan at GLA University, Mathura, India. We will wait, okay, for next 2 minutes only. Some participants, some participants are okay joining this invited expert talk, and from 12 p.m. IST onwards, okay, we will start our talk. Good morning, all of you. So now, Aditi ma'am, okay, we can start. Please go ahead, Aditi ma'am.
Sir, my voice is audible?
Yeah, you are audible.
Okay, so we should start the session. So, a very warm and overwhelming afternoon to you all. I, Aditi Saxena, on behalf of IQAC and Research and Development Cell, GLA University, Mathura, India, welcome you all to this invited expert talk on Introduction to Computational Modeling of Molecules and Periodic Structure, delivered by Dr. Armaković for different material groups running in different departments of university. As some of the audience or spectators were not available at the first session of this expert talk, so I would like to make them easier to know Dr. Armaković again. So I am briefing now some of his expertise and achievements from a huge bunch of what he has gained till now. Is the slide is visible with what I'm sharing?
Yes, it is visible.
Okay, thank you. So, Dr. Armaković was born in Sremska Mitrovica, Republic of Serbia. He is currently serving as Board President Association for the International Development of Academic and Scientific Collaboration and in Faculty of Science, Department of Physics at University of Novi Sad, Republic of Serbia. He is an active member of USAID Research Technical Assistance Center. Apart from his doctoral achievement in 2014 from the University of Novi Sad, he has published more than 116 SCI and Scopus research articles with around 2,000 citations with H-index 24. He is verified Publius reviewer with more than 300 pre-publication reviews in the reputed scientific journal and has been recognized as top peer reviewer. More than 80% of his published papers have been written with the collaboration of foreign researchers. He also initiated the establishment of the Association for the International Development of Academic and Scientific Collaboration, that is a non-government and non-political organization dedicated to the students and young researchers. He has more than 10 different ongoing external government and industries funded research projects and grants under the various ministries for scientific and technological development, modeling, and simulation. In the past session, an overview was given on how to design a structure of a good research paper. Now in this session, he will be molecules and periodic structure is. So now I'm requesting Dr. Armaković to leave the attention of audience to himself.
Thank you very much. I will now share my screen. Good morning to everybody.
Yes.
Good afternoon.
Good afternoon.
Can you please just allow me to share my screen?
Yes, sir. Wait a minute.
Aditi ma'am, just click on the name of Dr. Stevan. Okay.
Yes, sir.
In there is a tab. Okay, more. So by pressing that tab, okay, you can transfer the rights of co-host to Dr. Stevan. Yes, now Dr. Stevan, you can share your screen.
Yes, thank you. Okay, so can you please confirm that you see my screen?
Yeah,
Yes,
it is visible.
your screen is visible. We can.
Yes, thank you very much. Thank you very much for the lovely introduction once again. It is my great honor and pleasure to serve today to this joint event between GLA University and AIDASCO. And as in the previous lecture, I would like to mention that this lecture is intended especially for students and young researchers who are interested in some fundamental elements of computational modeling of molecules and periodic structures. So it is my great pleasure and honor to participate in today's event. And I would like once again to use this opportunity to thank the Professor Kamal Sharma for initiating and organizing today's event. I would like to also thank once again to Dr. Pradeep Singh for his efforts in this organization of this event. And also I would like to mention Professor Ruby Singh, who initiated this collaboration between GLA University and AIDASCO. And of course, Aditi, man, thank you very much for the lovely introduction and for serving as a host in these events. So today's lecture is focused to the applications of computational methods for investigation of molecules and periodic structures. And computational modeling of molecules and crystals, when I say periodic structures, I mean on crystals. It is very interesting and vibrant research area. And when I started to practice this scientific area at the University of Novi Sad some 12 years ago, it wasn't so popular at the University of Novi Sad. And the University of Novi Sad is relatively big university with more than 50,000 students. So I was amazed by the fact that no one is practicing computational modeling on all relevant levels of theory. And that is when I saw my opportunity, and that is the moment when I practically introduced this type of research in a systematic way at the University of Novi Sad. So today it is my great pleasure that I can share some of my experience in this area. Before I start with this lecture, I would like to mention one thing, and that is that it is, of course, impossible to mention all the relevant things regarding computational modeling, but if any student, if any colleague, if any young researcher is interested for collaboration or to get more information from me or my collaborators here in Serbia, please write to us. We will be it will be our pleasure to share all of our experience and knowledge to you, and we hope to make this collaboration systematic so that we can provide computational modeling services for GLA University for whoever needs our expertise. So, for the beginning, I would like to travel back in time a little bit, and I would like to take you to the year of 2009 and present you one of the first, if not the first, image of a molecule. So in the year 2009, researchers from IBM research group published a first image of a molecule. It was an image of a pentacene molecule, which is a well-known molecule in organic electronics. They used atomic force microscopy to obtain this image, and this is one of the first, as I said, if not the first image of a molecule. 3 years later, they acquired the first images of molecules which indicate the charge distribution within molecules, which was another great achievement by this group from IBM research. And they again used the atomic force microscopy. As you can see, these results have been published in fantastic journals with very high values of impact factor. This result was published in Science, this was published in Nature Nanotechnology, and it was really a breakthrough in science of molecular imaging. And later, great results were presented to the scientific community. In 2013, we received first images of molecules indicating the formation of bonds between atoms. Again, atomic force microscopy was used at the Lawrence Berkeley National Laboratory. And then the same group from IBM Research published a first image of PTCDA molecule, also a well-known molecule in organic electronics. And this time, they applied atomic force microscopy at room temperature. Now, I could carry on with the similar images for probably an hour. And now I want to explain why did I present these images. So, as you can see, these images are called images of molecules, but as you know, these are not direct images. These are not images as we would take with our own cameras. For example, as I can take an image of my friends or something like that. These are actually images of some properties that are expressed by molecules when they are found at, under certain conditions. So these are not, let's call them direct images. So because we cannot directly see molecules, we can only see some properties that they exhibit under certain conditions. We still need models and modeling. So for all of these images that I have shown to you in 2 previous slides, I have made an inserts from papers where these results have been published, and you will see that in all of these papers, no matter how sophisticated experimental setup we had to make an image of molecule, the researchers have used computational modeling of molecules. In other words, you will always in these types of paper found sentences like where they state that they have applied ab initio density functional theory calculations. So this is an insert from that paper published in Science. They state that they have used ab initio density functional theory calculations. This is an insert from the paper published in Nature Nanotechnology. You see these wonderful and breakthrough images of molecules. They also perform density function theory calculations to verify that intramolecular distribution of charge has happened. So once again, in that third paper, in that third set of images that I have presented, again, calculations using ab initio density function theory provide additional support for the proposed reaction pathways. So no matter how sophisticated equipment we use to make images of molecules and crystals, we still have to rely on computational modeling of molecules by quantum mechanical or some other methods. So that was the purpose of these several slides. I wanted to express the fact that we still have to use models, because we still cannot directly make an image of a molecule. We can get an insight into the structure or into the reactivity of molecules, but we still have to perform computational modeling. So when I say computational modeling, I think on DFT calculations, I think on terms like ab initio or something like that. And in the next few slides, I will explain those terms in more detail. So it is clear that if we want to computationally investigate molecules and similar systems, we have to apply certain theory to our model. So in the beginning, we have a structure, we have a model of a structure, and if we want to perform a computation or some kind of calculation on that structure, we need to apply some kind of theory. So all of the theories that can be used for computational modeling of molecules and crystals can be divided into 3 large groups. So initially we have quantum mechanical methods. When we use quantum mechanics, we actually treat molecule as a quantum mechanical object, so that the laws of quantum mechanics are applied on the molecule, and this type of methods for computational modeling is frequently called ab initio, which means from first principles, and it is very widely applied theory for calculations on molecules and crystals. After quantum mechanical methods, we have the so-called semi-empirical methods. These are just some examples of semi-empirical methods. There are dozens of semi-empirical methods, and this research area is also very vibrant. So for these methods are also relying on quantum mechanics, but with additional approximations and parameterizations. And last but not least, we have the molecular mechanics methods. Within this picture, we treat molecule as balls connected with springs, and this is a rather simple model, but also very powerful, because we can use this level of theory to investigate very large systems such as proteins. So let us go through all of these methods, and the purpose of this part of the lecture is to introduce you to to the areas which can be covered by these computations. And it is also purpose of this part of the lecture to understand which level of theory should be used for which area. So while quantum mechanical methods are the most accurate and while quantum mechanical methods are the most powerful and accurate methods, they are computationally very demanding, so they cannot be applied for large systems, for example, and we will see which method can be used for which area. So let us start by quantum mechanical methods. So the state of the quantum mechanical object is described by the so-called Schrödinger equation. This equation was introduced by famous Erwin Schrödinger, and it is practically it is a fundamental element of quantum mechanics. I think that I don't have to take too much of your time to explain how important Schrödinger equation is. So the quantum mechanical methods are actually based on how to solve Schrödinger equation for certain elements and certain molecules. So by applying quantum mechanical methods, three large groups of methods arise. In the beginning, we had the Hartree-Fock method, although it is one of the simplest and, if not the simplest, and the oldest methods, it is very powerful method. And as you can see, ab initio means from first principles. What does that mean, from first principles? It means that calculations that you perform are based on pure theory. So there are no empirical approximations, there are no adjustments of equations, just a pure quantum mechanics and some, of course, approximations, but non-empirical approximations. So Hartree-Fock method is a method to determine the wave function, to find the wave function of your system. And once you find the wave function of your quantum mechanical system, you can extract different properties from wave function. For example, you can receive information about the charge distribution and so on and so forth. The problem with Hartree-Fock method is that it doesn't take into account the correlation between electrons. And that makes troubles with some rather complex molecules, and that is the main limitation of Hartree-Fock method. After the Hartree-Fock method was introduced, the density function theory method came in, and it is certainly the most frequently used quantum mechanical method for calculations on molecules and crystals. Definitely the most widely applied. So what is the specificity of density functional theory of the DFT approach? Well, instead of dealing with wave function, we are now dealing with electron density. So the electron density is used for determination of the ground state of the molecule or crystal, and that is good because electron density is something that you can measure experimentally. It is something that you can observe experimentally and check your results. So in case of the wave function, you cannot measure the wave function. Indeed, you can extract properties from wave function theoretically and then compare with your experiment, but electron density is something which is directly measurable. So that was the main motivation to develop and define density function theory by famous Walter Kohn and Shah. Structurally, it can be said that it is similar to other quantum mechanical methods, but instead of the wave function, we deal with the electron density. What is the problem with density functional theory? Well, the exact functional is unknown. There is no such thing as universal functional, which can be used for all molecules, for all types of crystals. So we have to use approximations. What that means in practice is that we have really large number of functionals which can be used for DFT calculations. So what it means to have a functional in DFT calculations, I will come to that later. But I just want to mention that we have really a large number of functions which can be used for calculations. That is a problem from one side, but from the other side, it is very good because the area of developing new functionals is constantly on. So it is quite likely that you have already defined functional for all of your needs. And then we have post-Hartree-Fock methods. So as I said, the problem with the Hartree-Fock method is that it doesn't take into account the correlation between electrons. So one of the ways to take into account the correlation between electrons is to apply perturbation theory to Hartree-Fock methods, and that is the way how we could how we actually introduced electron correlation, how we took into account correlation between electrons. Of course, density function theory takes into account the correlation between electrons, and that is the main reason why DFT is more powerful, more usable than Hartree-Fock. Post-Hartree-Fock methods, since they apply perturbation theory, they are more demanding in terms of computational time. So it is quite likely that you will not be able to treat with your own computational resources large molecules with post-Hartree-Fock methods. So these are the main the three main groups of quantum mechanical methods that are used for computational modeling of molecules and crystals. Let me just mention that there are dozens of methods in each of these groups. There are all of those. It would take too much time just to mention all of the for example, functionals that can be used for DFT calculations and post-Hartree-Fock methods. So just remember that these are three main groups, not all of the types of calculations that can be done, just main groups. So after the quantum mechanical methods, the researchers, the scientists realized that quantum mechanical methods take too much computational time. So when these quantum mechanical methods were introduced, the researchers had to invest a lot of resources into getting computational power, and they realized that it would be beneficial if somehow those quantum mechanical methods could be additionally approximated, and it would be very beneficial to somehow shorten the time that is necessary for calculations to be done. So that is when semi-empiric methods came in. So in the area of semi-empiric methods, we actually again solve the Schrödinger equation, but we use empirical approximations. So what do we use? We examine a very large amount of experimental results. So we know what are the typical bond lengths, and we somehow parameterize and adjust these quantum mechanical equations in order to reproduce the experimental results. So that led to the so-called semi-empiric methods. So the main characteristic of semi-empiric methods is the fact that they are 2 to 3 orders of magnitudes faster than the standard DFT methods. And for example, for geometrical optimization of a molecule, you can optimize it, for example, with quantum mechanical method in a few hours, or you can optimize it with semi-empiric method in a matter of just a few seconds. So that is how that is why these methods are so important. Of course, accuracy and efficiency. Regarding accuracy and efficiency, the semi-empiric methods are not as accurate as quantum mechanical methods are, but the fact that they are 2 to 3 orders magnitude faster certainly emphasize their importance, because although they are not very, very accurate for calculations of different properties, they are very efficient, they are very fast for example, for geometrical optimizations, which is very important part of computational modeling of molecules and crystals. So what are the main semi-empiric methods? Everything actually started with NDDO methods. Those methods are actually based on the neglecting of the atomic differential overlap. So MNDO and CNDO are just flavors of NDDO and reparameterization, and the reparameterization has been performed in comparison to the pure NDDO. These are Hartree-Fock based semi-empiric methods, which means that approximations were empirical approximations had been incorporated into the pure Hartree-Fock method. After the NDDO family of methods. The Austin method 1 method came. That is actually the MNDO based method with improved nuclear core repulsion, and this method has been also reparametrized in comparison to the pure NDDO, and it was also a very important semi-empirical method when it came to the when it became available to researchers worldwide. And PM3 series of methods was also and still is very important family of semi-empiric methods. They are still used largely, and these methods are defined to reproduce large number of molecular properties. And what is specific about this method is that they although they are semi-empiric, they are able to treat hydrogen bonds, which are very important in the area of biomolecules, as you know very well. So these methods are semi-empiric methods derived from, for example, from Hartree-Fock methods, but lately the semi-empiric method which has been developed most intensively is the so-called DFTB method. DFTB abbreviation stands for density functional tight binding method. So it is a DFT-based semi-empiric method, and it is based on the Taylor expansion of the energy with respect to a reference density. So I want to emphasize the fact that all of these methods depend on the accuracy and the applicability of these methods depend on whether the parameters for each element of periodic system have been developed. So, for example, the initial DFTB was applicable only to organic, for example, or organic molecules, but lately the parameters for practically all atoms of periodic system of units of periodic system of elements have been developed thanks to the German scientist called Stefan Grimme and his group. So DFTB now is applicable for almost all molecules that are possible to define. So it is very powerful method, much quicker than DFTB. So later we will mention why semi-empiric, and later it will be demonstrated why semi-empiric methods are so important. So after the quantum mechanical methods and semi-empiric quantum mechanical methods, the molecular mechanics methods have been introduced. So in this area, atoms in molecules are observed as balls connected with springs, and this is practically the part of the classical calculations. Why? Because we use classical equations for calculation of the potential energy of a molecule. So this is the general form of equation for the potential energy of molecule, and we know the general form of each of these terms. That is something that is that has been derived from classical mechanics, and that is the reason why this is the classical equation for the potential energy of molecule. So what is specific about molecular mechanics is that we adjust the values of these constants so we can reproduce the experimental results. And in order to do that, we have to analyze a really large amount of experimental data and to adjust these values of constants to values which will reproduce the experimental results. And that is called parametrization. And parametrization can be performed with respect to the experimental results or with respect to the quantum mechanical calculations. And when I say quantum mechanical calculations, I mean on calculations which are performed on the very high level of very precise quantum mechanical calculations. So these are the fastest calculations, but of course the accuracy depends on parametrization. The more experimental data we take into account, the more accurate our force field will be. Or the more quantum mechanical calculations are accurate, the more our force field will be correct. So As with functionals, in density functional theory approach, you cannot have universal force field. So you have to, for example, parameterize force field with respect to organic molecules. And then you have, if you want to use force field, if you want to use molecular mechanics on, for example, inorganic molecules or inorganic crystals, you have to derive a new force field for that type of crystals. If you, for example, deal with ionic liquids, you cannot use all force fields for the ionic liquids. You have to derive and define and develop new force field for ionic liquids precisely. So that is the drawback of this method. But what is very good is that research groups from all over the world have developed very, very good force fields for organic molecules. So this is very important for the area of pharmaceutical science, because in pharmaceutical science you want to investigate the interaction between drug molecules and proteins. So you will use force field or molecular mechanics methods to study those large systems. So these are the fastest calculations, and because we use the classical equation for the calculation of potential energy of a molecule, we can apply this method to a very, very large system, so very large molecules. These methods can deal with systems containing tens or hundreds of thousands of molecules. And with the development of molecular mechanics and force fields, the molecular dynamics came in. So again, atoms and molecules are observed as balls connected with springs. We have the general form of equation, but now we have that dynamical part. And how is that done? Well, the time is divided in discrete steps. And for each step, we solve the Newton equation of motion for each atom. So we apply this simple quotation mark simple equation, and for each time interval we get the forces which act on each atom, and in the next step we repeat that procedure again, and in the end we collect what is called trajectories of for each atom, and we actually can see how these molecules and atoms move, and we can analyze the motion of these atoms and molecules. So if we apply a suitable force field, we will see how molecules interact, how molecules move around each other. We can see, for example, how the drug molecule attaches to a certain protein, which is very, very important in pharmaceutical industry, especially in these days. So I want to make an analogy with, I want to mention right now the COVID-19 pandemics. So we have this race to derive, to make new and efficient vaccines. So the scientists, when they started producing vaccines for COVID-19, they first performed molecular mechanics and molecular dynamic simulations. I guarantee you that. And they used the state-of-the-art computational software to do that. And those two slides, so this molecular mechanics and molecular dynamics, those two things have been performed in order to make a vaccine and to make something which will eventually save the humankind from COVID-19. So, what is the basic protocol for computational modeling? So we have, in the previous slides, we have been mentioning several levels of theory. So if we use quantum mechanics for computations, or if we use semi-empiric levels, or if we use molecular mechanics, we call that a level of theory. So when you read a paper where computation modeling has been applied, you will find that term very frequently, level of theory. The researchers will report that they have been used certain level of theory for calculations. So in most of my research papers, I have been dealing with quantum mechanical levels of theory and with molecular dynamics level of theory. So from now on, I will be using the term level of theory, and when I say level of theory, I think either of DFT or on Hartree-Fock, or molecular mechanics, or to molecular dynamics. So, what is the basic protocol for computational modeling? The things presented in previous slides may be complicated for some young researchers or students which have not been dealing with quantum mechanics so far, but in principle, the basic protocol for computational modeling is very simple. You have the input file, you make the input file, you load that input file into the code. This is, of course, the code that you are using. And there are so many codes available. I will give you some important information about that. And then the code, makes calculations for you, and the code produces the output file. So you start with the text, you upload that text to the code, and you receive the text. So after you receive the output file, then you perform post-processing of that output file, and you can then receive various properties. For example, you can derive the structure of some protein presented here, or you can get the information about the charge distribution within the molecule, or you can see how how atoms of your molecule are interacting with water, etc., etc. It's actually in principle, it is very simple. You just have to know how to make this input file, and you have to learn how to post-process the output file produced by the code. Don't worry, because there are dozens of post-processing tools which can be used to analyze your output file. In neither case, you don't analyze the output case by yourself. Of course, if your calculation crashes for some reason, for example, if you didn't make an input file, then you will analyze output file by hand. You will see where the error is, but you're not going to in order to have this beautiful image of a molecule prepared, you are not going to have to do that by your own, by doing some additional calculations manually from the output file. No, there are tools which will help you to get this, and to get this, or to get this. So it is very practical area of research, necessary, in my opinion, necessary for each and every experimental group worldwide. So this is one typical example of an input file for the code called, this is computational modeling code called GAMES. This is abbreviation for the General Atomic and Molecular Electronic System Solver, and this term has nothing to do with video games, which computational physicists and chemists like to play from time to time. So this is an example of an input file, and this input file contains all of the information that this code needs to produce the output file. And when you see first time this input file, it may look rather complicated to you, but actually it is not complicated. It's not complicated at all. The makers of GAMES and makers of all other computational codes were very kind to make intuitive input files, to define input files to be easy to understand. So you have, for example, this sign here. This dollar sign indicates actually the beginning of each block, and we will go through one example of input file right now. Let's do that right now. So this is the example. So the point is to make somehow the input file, and then to upload that to a code, and then code will perform calculations and produce the output file, and then you post-process the output file with other external tools, or the tools with this code, and you will receive the results. So to generate this input file, you can write it on your own, and I must admit that I didn't know that great tools exist like this Avogadro program. So I started with molecular modeling by writing my own input files and wasting a lot of my time. Then I realized that I can use some programs for that. So that is what I wanted to share with you right now, because This is very nice and interesting program. Please, especially young researchers and students, remember this slide. Remember to type the Avogadro program and to search for it, and it is very useful. Also, the Avogadro program has been described in details in this paper over here, published in Journal of Cheminformatics in 2012. So please go through this paper when you have free time. And now I will show you how you can relatively easily make an input file with Avogadro program. So this is the Avogadro program, and this is the main window. So you can either import a structure, or you can select some of the elements here and draw your own molecule. This molecule has no sense. It is just for this molecule is just for the purposes of description, how to make a input file. So forget about the structure of this molecule. This is completely insane molecule that doesn't exist. So you go to extensions and you see that the makers of Avogadro have made possible to make input files for different molecular modeling and computational modeling codes, which is fantastic. So you go for GAMS, and you go to the input generator, and here is the how your input file will look like. So here you adjust various computational details. I'm not going to go through these computational details because it would take really too much time. I'm just going to click some of these options, and then I will just mention that each $sign designates the certain block which is required for running of GAMS calculation. So here we have demanded the optimization. We wanted the restricted Hartree-Fock method to be applied, and this is where we define what is called basis. And this block here is defining the structure of our molecule. So each input file for each and every computational modeling program for molecules or crystals has this block, and that is the structure. So these are just coordinates of atoms within this molecule with strange geometry. So once you select all of the necessary details, once you set up this calculation, you go generate, click generate, and then you have input file. Let's call it like this, GLA AIDASCO, and that is right now on my desktop. Let me just find it for you right now. So this is that input file. It contains input, it contains coordinates of atoms within this molecule, it contains information that are necessary for code. This is just some simple calculation. And the next thing that you have to do is just to type one command called run GAMS, and the GAMS will run calculation based on this input file, and you will receive the output file, and you will have everything that you need to perform investigation of your molecule. So let me show you when we are here dealing with files. Let me show you how one output file looks. So this is output file produced by the program called Psi4. It is also very important, very good code for calculations on molecules with different levels of theory. The makers of this program did a fantastic job. So this is how the output files look. So these are the information about the molecular orbitals here. Here you have the information about the structure. So here you have information about iterative procedure that has been performed in order to perform these calculations. And in the end, you have summarized some of the results. You extract these results. For example, from this output file, I need these results. But there are also some additional tools which will analyze this everything for you, and you will receive nice images for your papers and whatever you need. So this is how actually it is easy to run a calculation. It is easy to set up. We can use, for example, Gaussian is one more very popular very popular program for computation modeling of molecules and periodic structures. So here we can also see how these things change when we click here, and we click generate to generate the input file for this program, and everything works smoothly. I want to mention that this is commercial Gaussian. Gaussian is commercial program. You have to pay in order to use it. You don't have to pay to use GAMAS, Abenate, GAMAS UK, MOPAC, and YCamp Sci4, LAMPS, or Orca, or some other programs. So I will go through that also somewhat later. So this is how you can make, for example, the input file. So let's get back to the. So this is actually the first part of. Of this lecture. So if anyone has some question, feel free to ask right now. When we finish with questions, we will immediately go to the second part of this lecture. So I would be very happy to answer to your questions.
Thank you, Dr. Armaković, for your words and wisdom. Now I would request you all to ask the queries if anyone has, or else we will take a 5-minute break to proceed for the next part of the session at 1 p.m. IST. So if anyone has any query, they can ask now.
Hey, hello, Steven.
Hello.
It was very good presentation related to the molecular dynamics of the materials. Basically, I am working on the nanocarbides for catalytic applications. So I was trying to explore this theoretical work for my research purpose, and I was seeing that you are working on Avogadro. So
yes.
it is free source, or it is paid?
Yes. The Avogadro is completely free.
Okay.
That is the reason why I have made this slide. Here is in the lower right corner of the slide.
Oh, okay.
You can see. Yes, you can see. Yes. Well, now I see that the text is very small. I should have increased the size of the text in order to emphasize the fact. Yes,
it's fine now.
Yeah. So the Avogadro is completely free, and there are also some additional modules made by some other research groups because Avogadro is also free to be modified. So everything that you need regarding Avogadro, how to use it, I am at your service. Don't forget that. We will gladly share our experience and skills, whatever you need. So the thing is that there are commercial molecular modeling codes and there are free for academics codes. And I also prepared one more slide regarding that. So I will later mention some of the codes that can be used for molecular modeling for computations on both molecules and crystals. The thing is that serious research can be done with free tools. And I repeat, it is true. You can use free tools for serious research, for publication of papers. But the thing is that also that commercial solutions have additional functionalities, and it is much more easier to use with commercial solutions, and you can cover a much larger amount of work with using commercial programs. Of course, commercial programs, for them you have to pay certain amount of money, but it certainly and definitely is worth of it. And a lot of these commercial programs are actually involving some of these free for academics tools, and I will mention that later.
Those are damn expensive.
Sorry?
Those are damn expensive.
Well,
so it is better to use freelance sources.
It depends really, because some things cannot be done with these free tools, and it only depends how large amount of work you want to do. So, for example, commercial solutions have graphical user interfaces which allow you to work really quickly, and to for example, in a month you can do 10 times more of a work with commercial programs in comparison with free for academics. But that definitely doesn't decrease the importance of free for academics tools. They are definitely very powerful, and I'm using them all the time because they have some functionalities which are not present in the commercial solutions.
Okay.
So,
Thank you, Steven.
Thank you very much.
Dr. Armaković, I am Rishabh Chaturvedi. I am just asking about the accuracy of the Avogadro results as compared to the experimental results.
Yes. That is really a wonderful question, and thank you very much for asking that question, because I just want to make a point here. You don't make calculations with Avogadro. Avogadro is able to do some kind of calculations, but you don't actually perform calculations with Avogadro. With Avogadro, you make an input file for a computational code which you want to use. Regarding the calculations which you can do with Avogadro, for example, you can perform geometrical optimization with the force field with Avogadro. And this is, for example, what you can do with Avogadro. So, for example, if I'm having this strange molecule, this is a type of calculation which I can select force field, and then I can press start, and the program will optimize this molecule. So this is the optimized geometrical structure. What it means to be optimized, it means that we have found such structure for which the derivative of energy is equal to 0 with respect to each coordinate. So this is geometrically optimized structure. And for example, if you would perform a geometrical optimization with DFT code, it would take so much time to do this, much more time than in this case, and you would receive very, very, very similar geometrical information, a very, very similar structure of this molecule. So that is very good question. But unfortunately, you cannot apply this force field, for example, for some complexes, or you cannot apply this for crystals. So there is a very limited number of calculations that you can do with Avogadro. But Avogadro is not intended for calculations primarily. It is intended primarily for making an input files for these wonderful, mostly free modeling codes. It is also made. You can also make some. You can also generate periodic structures. You can work with unit cells. You can make a unit cell out of this and then make a crystal. So that's it. This force field will work very good, will do a great job with organic molecules, but with complex molecules and transition metals and stuff like that, it is not going to be efficient. But regarding your question, I will mention later, you will see I compared the efficiency of quantum mechanical methods and semi-empiric methods, and that slide will be, and those results will be very interesting for you. So thank you very much for asking this question.
Hello. Sir, I'm
So we have
Anas
one
Islam.
more question in the chat.
Hello.
Hello, yes.
Yeah. Yeah, I have a question to ask
Yes.
regarding GMS and Avogadro. Sir, can we run optimization on salt in Avogadro, which is drawn on Avogadro itself? And another question.
Sorry. So you ask if we can perform optimization of soil.
Yeah, salt. Means cations and anions. Yeah,
Sorry,
if
sorry.
if
Can
we
you?
can add charge on, yeah, if we can add charge on cation and anion in a molecule, so
Yes,
can
yes.
we run optimization for that?
You cannot do that in Avogadro, but you can prepare an input file for some of those codes and then run with some other code. Yes, yes, that is. You can define the charge on each atom, but that is a little bit. That can be a little bit tricky. Whenever you want to add specific charge on some atom, that can be a little bit tricky to work, and it is always easier to work on neutral molecules rather than cations and anions. And when you work with cations and anions, you have to be very careful regarding the level of theory which can be used, because semi-empiric levels can be a little bit inappropriate for such systems. So that is, whenever you work with cations and anions, that is um, uh, harder, and you have to use what is called diffuse functions when you work with cations and anions, because of the charge density, and I don't want to go in details because it would require a lot of time, but it is possible to make an input file and then select some of the codes and to run your calculation.
Okay, okay, sir. Sir, one small question
Yes.
regarding that. Sir, what is in your view, what is the best DFT functionals for high multiplicity metal cluster? Can you?
Yes, 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 yes. So that is very tricky question, because I have one slide later, and I will answer to that question on that slide. So
Okay, sir.
I would use that. That is very nice question. In a in a way, I anticipated and waited for that question, because students frequently ask that question. So of course there is no simple answer to that question, but I will mention that later. Thank you for
Okay,
asking that
thank you.
question.
Thank you, sir. Thank you.
Aditi ma'am, you can also take some queries from chat box. Okay, there is one more query, Dr. Stevan.
Yes.
Is it possible to build a molecular model? Is it possible to build a molecular model of carbon fiber sheet in Avogadro? And this is the query, okay, asked by Mr. Amit Kumar.
Yes, thank you very much for the question. Well, in a principle, it is possible. I don't see why that wouldn't be possible. It is, of course, just necessary to have some anticipation how that structure should look like. So, if it is some kind of carbon shield, then I would the first association to carbon shield is a graphene sheet for me in some of my experience. So yes, it is possible to define and to model the graphene sheet, and then to modify that graphene sheet, and that can, for example, that can be a model of carbon of a carbon shield. So it is in principle, I think that it is possible.
Okay, thanks a lot, Dr. Steven. Now I think, okay, we have covered, okay, all the queries, and uh, there is a, okay, 5 minute break, and our next session will be resumed, okay, from 1 p.m. onwards.
Okay, okay, that is in 2 minutes. Yes.
Yeah, yeah.
Yeah. Okay. Okay. See you in 2 minutes.
No, Dr. Steven, we will take 5 minute break, and we will start our session. Okay, next session from 3 p.m. Okay, IST onwards.
Okay.
Okay.
Okay. Okay. Thank you.
Thank you, Dr. Steven. Thank
Thank
you.
you. See you soon.
Hey, hi, Stephen. Meanwhile, people are joining our call. So, can you please tell me in brief that all the functions which are being used in Avogadro, so each and every tutorial is available, or we have to refer any other book or any other video or any other tool to use Avogadro for beginner?
Yes, well, I think that there are a lot of examples on the YouTube, and there are a lot of information on various websites. But what is specific about Avogadro is that you actually don't have to use tutorials for Avogadro directly, because Avogadro gives you the possibility to make an input file. So you are not going to refer to the tutorials regarding Avogadro for those input files, but you will refer to the tutorials regarding the specific computational code you want to use. So for example, if I want to make an input file for some molecule, Avogadro is very simple. You just press for which code you want to use, you want to make input file. So if I want to make an input file, for example, for Mopac, this is what I'm going to receive. So if I don't know how to define the input file for Mopac, I'm not going to search for the answer at the documentation for Avogadro. I'm going to take a shot on the Mopac website and to learn what should I write here in order to make my input file suitable for the Mopac calculations.
Okay.
So all of these programs are well documented, especially the most frequently used, GAMS or the Gaussian, which is commercial. So all of them have fantastic documentation, And of course, for everything that you need, I'm here to help together with all other members of AIDASCO. So I just want to say it is not necessary to work in the dark for in the start, because we can provide all of the necessary. We can have some further workshops later how to use everything of this.
So nice of you.
It's pleasure. It's our pleasure.
Thank you, Steven.
So as all the queries has been asked, so we may now proceed to the next part of the session. So I would request Dr. Armaković to please start the next part of the session.
Thank you very much. So this is the last slide which we have discussed, and we saw how to make a simple input file for GAMS code using Avogadro. What we are going to do next is to see what is the basic protocol. We are going to introduce ourselves with details of the protocol for computational modeling. So when you want to perform calculations on some molecule, for example, or some crystal, this slide, these several next slides are very important for you, because they will introduce you with what you have to do in order to perform calculations successfully. When you load your favorite modeling program, you have to somehow generate the structure. You have to either draw the molecule like I did, like I draw that funny molecule, or you can import the molecular structure from some of the databases. So the chemical space is so large. There are hundreds of millions of possible molecules. And if you want to, for example, study some antibiotic, or if you want to study the reactive properties of some drug or some organic molecule, the chances are very good that the structure of that molecule is already deposited somewhere. So there are dozens of databases from which you can download the structures of your molecules or crystals or proteins. And I didn't mention them here because that would be too much of information for you, but we can leave that for some other workshop or webinar or lecture. And I will introduce you with those databases. Initially, when I started to practice computational modeling, for the first month, I manually have drawn all of the molecules, which was very tedious and time-consuming process. Then I realized that there are databases containing millions of structures. So you can download one structure, you can download 10 of structures, you can download thousands or millions of those or millions structures of data or of molecules. So if you want to deal with molecules and if you want to import molecular structure to your modeling program, then these are the file types which you will find most frequently, with which you will deal most frequently. X, Y, Z, those are just simple coordinates of atoms in molecule. These file types will preserve the information about the bonds. So here all bonds will be single bonds between atoms in molecule. In this case, you will preserve the information about the bonds. So if there is a twofold bond, or there is a double bond or triple bond, these file types will save that. If you are dealing with periodic structures, you will import, or you will save your structures, or you will save the structure of your unit cell in a CIF or MMCIF files. CIF is actually a abbreviation for crystallographic information file. This type of file for periodic structures is very important in modeling, because when scientists solve the crystal structure of some material or some protein, they save and deposit that structure in this file format, so you can import that in your modeling program. Avogadro can deal with all of these file types and with these file types and with these file types. So you are just a step away from making an input file for your own research on molecules or periodic structures or proteins. So PDB is an abbreviation for the Protein Data Bank. There is a website called pdb.org where you can download thousands of structures of proteins, and PDB database was very popular when unfortunately COVID pandemic struck us, because very soon researchers from, I think, China reported the crystal structure of the COVID-19 protein, which was most responsible for the spreading of infection. So researchers all over the world immediately started to perform molecular docking and molecular dynamic simulations using that PDB file. So literally, you are just 2 clicks away from the protein data bank, from the protein related to COVID, and from your own research, from your own research on these molecules. We can leave that for some other workshop, because that would be a lot of information right now for especially young researchers and students. So the next thing we should, that is the first step. We draw, or we import the structure of a molecule or crystal which we want to investigate. Then the second task is to define which method we want to use on our for our calculations. And as I mentioned earlier, we can do quantum mechanical calculations, we can do semi-empiric calculations, or we can do molecular mechanics or molecular dynamics. I placed molecular mechanics and molecular dynamics in the same area because they are based on the force field, but in this step you just select which level of theory you want to use for your calculations. So the next step is to specify the computational details related to your level of theory. So if you want to perform quantum mechanical calculations on your molecules or crystals, you will have to define which functional should be used, which basis set should be used, what should be the convergence criteria for these calculations. And of course, there are many other computational details which you have to define here. I have placed only these 3 because these are the most important, but trust me, there are some more computational details. In case of the semi-empiric calculations, you have to make a proper selection of parameters for atoms. Remember that there are no parameters for each and every atom. But lately, thanks to the work of Professor Dr. Stefan Grimme from Germany, we have a fantastic source of parameters for all atoms for semi-empiric calculations. And in case of the molecular mechanics and molecular dynamic simulations, you have to define, regarding computational details, you have to define force field, you have to define the simulation time, time step, and temperature. So that is very good with molecular dynamics and molecular mechanics, because you can introduce the effects of temperature, but we will mention that later. So once you defined these computational details, I want to introduce you with some details regarding quantum mechanical calculations, because when you teach at the university level, most frequently everything starts with quantum mechanical calculations. So for quantum mechanical calculations, if, for example, you want to perform density function theory calculations, you have to make a proper selection on functional. So these are just some of the groups of functionals that are available. And there are, for example, regarding hybrid functionals, there are dozens of possibilities. There are hundreds of possibilities for regarding functional. Once you define the functional, if in case of DFT calculations, of course, you have to define the basis set. And as with functional, you have so many possibilities for defining basis sets. That is the prerequisite. By defining the functional, you actually tell the computer code how to calculate the total energy of a system. And by defining the basis set, you actually give input to your code how to generate the molecular orbitals and how to deal with the charge distribution around atoms. So these are the two main parameters that have to be defined. And now I would like to use the opportunity to answer the question that one of the colleagues asked, and that is which functional or which level of theory should be used for high multiplicity materials, for molecules with high multiplicity. So there is no straight answer. There is, as I said, there is no universal functional for all problems in molecular modeling. So what I would do in that, so what scientists should do in that situation, they should perform calculations with several functionals, and then check in literature, is that data are the results that he or she obtained are reasonable. And that is why my previous lecture is very important, because you have to know where to search for those good papers and how to find those good journals. So that is one thing. You should perform with your calculations with more than one functional. And in that particular case, I think that hybrid functionals would be the most reasonable choice, because in hybrid functionals you have the combination of exact exchange and correlation. So there is a really large number of hybrid functionals which are defined in that way to cover some specific type of molecule or some specific type of crystal. In that particular case, I saw a few papers where Minnesota family of functionals were used. Those are the MO6. Later, now we have defined an MO8 functionals. So the B3LYP functional, this one here, is the most popular density functional used. So if you check the number of citations for that paper, the B3LYP was practically defined by Professor Axel Becke, and that paper is cited more than 120,000 times. So it's fantastically large number of citations. So B3LYP is mostly is doing a great job with organic molecules. It is remarkable with some other molecules and nanostructures. And if you want, for example, to study the fullerene or nanotube, or so, you can apply B3LYP. When it comes to this is the most popular functional when it comes to the molecules. But when it comes to the periodic structures, when it comes to the crystals, PBE functional is the most frequently used. So the final answer to that fantastic question is go with B3LYP for the start, because you never know what B3LYP is going to is going to provide. Sometimes it performs for some specific structures. You cannot expect the B3LYP will always perform good. But I like to perform my calculations with B3LYP firstly, and just out of the curiosity to see what is going to happen. But for those purposes which are mentioned, some other, for example, Minnesota density function should be most probably performed. But as I said, these are just some of the main hybrid functions that are mentioned. There are dozens of more, and that question requires deep inspection and literature survey. So we can leave that. The more detailed answer can be left for some other occasion, or some, for example, workshop. I would also like to mention the long-range corrected functionals, which are good for excitations, which have been developed to deal with excitations. For example, if you want to simulate the ultraviolet spectra, you will most probably want to use long-range corrected functionals. And there are so many information about density functionals and basis sets, of course, but that is we should leave that for some other occasion. So after the functional, for that specific question by a colleague, it is also important to mention the basis sets. For molecular structures with high multiplicities, it is necessary to involve diffuse functions on at least heavy atoms. You can introduce diffuse functions on light atoms, such as hydrogen as well, but for those calculations, diffuse functions are a must for heavy atoms, and heavy atoms are all atoms that are not hydrogen in computational modeling of materials. So definitely not just when you say the level of theory, it is not just the functional, it is also the basis set. And of course, this is just for the density functional theory. So this was the first initial answer from the aspect of DFT calculations. But high multiplicities and all other tricky and difficult properties should be also treated with post-Hartree-Fock methods, which are not mentioned right here. This is only relevant for DFT calculations, but to complement the answer to that question, you should probably also try with post-Hartree-Fock method, for example, the CCSD method, and the thing with this with the modeling is that if you deal with rather complicated structures, it is difficult in the beginning to identify the right level of theory, but that can last for months sometimes. But once you identify the right level of theory, and once you identify the suitable set of parameters regarding computational details, you know where to start for any other molecule or structure which is similar to that molecular structure. So it is worth of it if you spend a lot of time to identify the true level of theory. So once we have defined these computational details, functional basis set for DFT calculations, for example, then you define and then you choose what type of calculation you want to perform. And in case of quantum mechanical calculations and semi-empirical calculations, you can run geometrical optimization, you can run single point energy calculations, or you can run a property calculation. So what is geometrical optimization? Well, as I said before, all systems in nature tend to have such structure in which their energy is the lowest. That is one of the fundamental laws of nature and laws of our universe. So geometrical optimization means to find such structure in which the first derivative of energy is equal to 0 with respect to all coordinates. In other words, we find such geometry of a molecule in which it has the lowest energy. And mathematically, it is the first derivative of energy with respect to all coordinates equal to 0. Geometrical optimization is an iterative process as a single point energy calculations as well, because you firstly calculate the energy of your current structure, of your current geometry, and then you perturb a little bit that geometry and then calculate the energy again, and you repeat that process until you reach such state when the difference between energy is so small that can be neglected. And that's how small that difference between energy or some other parameter is defined by the convergence criteria which I mentioned here in the computational details. If you want to perform geometric optimization, then you will select there to geometrically optimize your molecule. Or if you are interested only in an energy of that precise and single geometry of a molecule, then you will run single point energy calculation. And if you want some particular property, for example, charge distribution, some spectral property, or something else, then you will order the molecular code to run a property calculation. It is very important to mention that property calculations should be performed only on geometrically optimized molecules. So, just to go back to this funny molecule, I'm not going to perform geometrical optimization on this. Let me just perturb it. So this is unreasonable geometry. And if I calculate some property on such unreasonable geometry, the results I will receive will be useless. So you always have to firstly geometrically optimize your structure. And once you geometrically optimize it, then you can run property calculation. The code, most frequently, the code will be able to give you some result if you calculate on such unreasonable structure. The code will present you some kind of result, but that is not going to be relevant because it is not calculated with respect to the lowest energy geometry. This structure is obviously far, far away from its equilibrium state. And if your geometry is far from equilibrium state, the most likely scenario is that your calculation is going to be broken, is going to crash, because this leads to unreasonable set of parameters which cannot be dealt with. So if you're using semi-empiric calculations, if you're using semi-empiric level of theory, you can practically do the same type of calculation as with quantum mechanics. But of course, if geometrical optimization and single point energy calculations and property calculations are not going to be as accurate as in the case of quantum mechanical approach. But we will deal with that later, why it is important to have semi-empiric and to apply semi-empiric levels of theory. And if you want to perform molecular mechanics or molecular dynamics, the type of calculations that are available is minimization, which is similar to geometrical optimization. You want to minimize the system with respect to the energy. You can perform dynamics to check and to obtain the motion of each and every atom of your system, or you can simply check the temperature dependence and see how your system behaves under different temperatures. I just want to make one important point here. When geometrical optimization provides the lowest energy geometry, you have to check if it is a true ground state or not. And how do you check that? You do that by vibrational calculations. You calculate the vibrations. You actually, in that case, you actually deal with the second derivatives of energy with respect to all coordinates. And as you remember from mathematics, the first derivative provides you with the extreme points, and the second derivative with respect to coordinates gives you information about whether that is local minimum or local maximum. So as you can see, quantum mechanics, molecular modeling is a very and highly interdisciplinary field which incorporates mathematics, physics, chemistry, informatics. There is a lot of programming in computational modeling, and every now and then when you use computational modeling, you realize that you want to write your own scripts to investigate something later. So you have to, at one point in time, you realize that you want to that it would be highly beneficial if you learn some programming language like Python or C, and that's it. So once you specify the type of calculation and the code ran your calculation, you then receive, as we have seen, the output file, and then comes the post-processing of the results. So what can you receive? What type of results you can obtain with post-processing? Well, in case of quantum mechanical calculations and semi-empiric calculations, you can get the information about, for example, charge distribution. You can get information about atomic charges, dipole moments. The list is countless practically. Regarding spectroscopy, you can simulate the infrared spectra, the NMR spectra, ultraviolet, Raman, and some others. And regarding molecular dynamics, you can calculate the so-called radial distribution functions, which will give you probabilities to find, which are used to analyze the motion of, for example, molecules of water around atoms of your molecule which you investigate. You can investigate various you can calculate various thermophysical properties. For example, you can, for polymers, you can calculate the glass transition temperature, etc., etc. These are just some properties which you can get by post-processing of the results. The purpose of this slide, the purpose is just to get you a small insight how this protocol works, what am I doing practically for living when I sit by the computer. So these are the steps that you take. And as you can see, there is a lot of steps. There is a lot of details which should be covered. But after dealing with this some time, you get the feeling, and you can feel practically the motion, and you realize this is very powerful area in which you have to track how it develops. You always have to read new papers to seek new levels of theory and to seek how to calculate new properties, because every now and then you will have some collaborator which will need something regarding your calculations which you have never calculated before, and that means nights and nights of not sleeping and trying to find the right calculation and the right level of theory. But that is why this area is so vibrant and exciting. So here are the tricky questions. And usually when you try to explain to somebody what is level of theory, how to perform calculations, one of the first questions is, what is the best level of theory? And what is the best density function? And what is the best force field if you don't want to perform quantum mechanical calculations? Or what is the best computational modeling program? And these are simple questions, but the answers are not simple. Or we can have the universal answer to all of these questions, and that is that it depends. It really depends on what type of molecule or crystal you're dealing with. It depends on how large your system is. Regarding the best computational modeling program, it also depends for what you need, because some developers, it is impossible to have the perfect modeling program which will cover all the relevant levels of theory, which will be usable for all types of structures which can be modeled, But after some time, there are some hints, and you realize what are the trends, and there are some rules which you follow, and you don't have problems. Use quantum mechanical methods for small or medium-sized molecules, and when you want to obtain accurate properties. When you want to calculate properties of molecules with high accuracy, the quantum mechanical methods should be used. You can use them for unit cells. You can use them for, of course, molecules and crystals. On average workstation with several tens of gigabytes of RAM and 16 or 32 processors, you can deal without problems with molecules and unit cells with up to 100 atoms. And medium-sized molecules are defined as molecules with around 30 carbon atoms. but it really depends if you have, for example, complex molecules. Complex molecule can have, for example, 50 atoms, but it can contain transition metal elements, or some tricky elements with a lot of with a high number of electrons. So then the number of atoms in your molecule is not so relevant, because if you have complicated and tricky elements in your molecule, then it would require, a lot of time. And quantum mechanical methods, of course, we would like to be able to use quantum mechanical methods for all structures, including the large one, but the computational cost of applying quantum mechanical methods is what prevents us to use them to apply them on very high, on large structures. So that is when we use semi-empiric methods. We use them for large molecules or unit cells. Semi-empiric methods have proven to be very, very useful for organic molecules and periodic structures. And we can use semi-empiric methods to pre-screen selected properties, or to pre-optimize some molecule, some large molecule. And we will have one nice demonstration of that. And use molecular mechanics methods for very large structures, such as proteins. So it would be impossible, even with the strongest computer in the world, to perform geometrical optimization of a protein, because proteins can have thousands of atoms. And it is impossible to apply quantum mechanical methods, even the semi-empiric methods on them. It is possible to perform quantum mechanical calculation on a fragment of a protein, and to use quantum mechanical level on a fragment of a protein, and to use the molecular mechanics method on the other fragment of the molecule. That is possible. And you can use molecular mechanics to explicitly take into account the solvent. In case of the quantum mechanical methods, to explicitly take into account the solvent molecules, that would mean that you have to place for example, water molecules around your molecule, and that would increase tremendously the cost of your computation. So that is not practical to apply quantum mechanical methods for explicit take into account of solvent, but it is possible to take into account indirectly the effects of solvent in quantum mechanical methods, and use molecular mechanics or molecular dynamics to take into account the effects of temperature. So it is not possible to do that efficiently with quantum mechanics, but if you want to check how your protein or how your molecule interacts with some other molecule on different temperatures, then you will use molecular dynamics or molecular mechanics. And let me also mention that there is possibility to use the combination of quantum mechanics and molecular dynamics, where the dynamics is investigated in the standard way as in molecular dynamics methods is, but the energy is calculated in the quantum mechanical method. That method is quicker than quantum mechanics, but slower than molecular mechanics, and it is useful for investigation of interaction between some complicated molecules. But we will leave that to some other occasion. So we have so many different levels of theory, and each level of theory is good for something, but there is no universal level of theory which will be good for both small drug molecule and, for example, for some large protein. So it is very wise to learn how to combine levels of theory, and we can combine levels of theory to improve our efficiency, or when we have to investigate a very large structure. So let me demonstrate this. So let's say that we have some molecule which is very far away from its ground state. So here is the benzene molecule, here on the left, distorted, and this geometry it is totally unreasonable. And we can say that this molecule has high energy because it is far from equilibrium state. We know how a molecule of benzene should look like, and we see that this is far, far away from that. So to geometrically optimize this distorted structure on quantum mechanical level of theory, it would require a certain amount of time. Of course, on some older computers, it would take an hour or two. On the new computers, it would require several minutes. But what can we do? We can firstly optimize this molecule with molecular mechanics or semi-empirical level of theory, and we will receive this. This is not as accurate as possible, but this is still much more closer to the true ground state of benzene. So in the first step, we use molecular mechanics to geometrically optimize this structure and to receive a structure of a molecule which is much closer to true ground state. Then we use this as an input to perform quantum mechanical geometrical optimization. And in that way, we save a lot of time for our calculations. So this is an example for a very small molecule. And this molecule is so small that we can use whatever level of theory we want. Because it is small, the calculations will last for a small amount of time. But if we have some large structure, it is very inefficient to immediately run quantum mechanical optimization. So it is always the best thing to pre-optimize with molecular mechanics or semi-empirical level of theory to get the more reasonable geometry of that molecule, and then to apply the quantum mechanical method to geometrically optimize it, to re-optimize it, and to get the relevant geometrical, to identify the true ground state. And once we have the true ground state, we can use that true ground state for our calculations of properties. And that can be charge, distribution, spectroscopy, reactivity, and God knows what has been so far defined for property calculations with molecular modeling. So that is the use several levels of theory. Here is one more nice example how to where we should combine levels of theory. So we should combine levels of theory when we have to investigate a very large number of structures. For example, let's consider a molecule with many possible conformations. We know that complicated molecules can have a large number of rotable bonds. That means that there is a high number of conformations. And even though that one single conformation can be treated with quantum mechanical level of theory, if we have hundreds of such structures, it is very time-consuming to optimize them on quantum mechanical level of theory. So what we will do, we will use molecular mechanics level of theory to generate conformations and pre-optimize them with force field, just like in the previous slide. And that will give us more reasonable starting geometries for calculations and optimizations at higher level of theory. Then we can use the semi-empiric level of theory to re-optimize them and to practically enable narrowing the number of relevant conformations. Because if we have hundreds of conformations, after these two steps, we can take, for example, 20% of those, all of those generated conformations, because we can take the conformations with the lowest energies. We are not going to deal anymore with conformations which are unreasonable or have unreasonably high energies, and we can pre-screen them with semi-empiric level of theory. And once we see what are the best candidates for lowest energy conformations, we can re-optimize them again on the quantum mechanical level of theory. And when we re-optimize them on quantum mechanical level of theory, we can calculate all the relevant properties at even higher quantum mechanical level of theory. And in that way, we will be able to not only obtain required properties, but we will definitely shorten the time of our research. So if we wouldn't use combination of levels of theory, for example, if we would have a some medium-sized drug molecule with around 30 carbon atoms, and if we would like, for example, to calculate the dipole moment of that, of all of those conformations, it would, to use just a quantum mechanical level of theory, it would require days. But if we would combine levels of theory, we can finish everything in just a matter of a few hours. Of course, it depends how large each molecule is, how many atoms it has, and which atoms it has. And of course, it depends on how many conformations are there. But I was curious enough, and I checked for one medium-sized molecule, for example, the propranolol molecule, and it has, under certain conditions, it can have a lot of different conformations, and we received 100 conformations or more, and with just a quantum mechanical level of theory, it took, I think, 4 or 5 days to screen all of the conformations, but with combination of levels of theory, it took several hours to finish everything. So it was very reasonable, and it is very wise to combine levels of theory. Of course, it is tricky sometimes to combine levels of theory because semi-empiric levels of theory and molecular mechanics are not always available for each and every type of structure, but still it is a good starting point to optimize them on lower levels of theory and then re-optimize them at quantum mechanical levels of theory, because these levels of theory will always produce much more reasonable starting points than the ones than the geometries that you have, for example, drawn by your own hand. So there was a question of, at one point I think that there was a question of whether to use free for academics tools or to use commercial tools. The good thing about computational modeling is that there exist literally dozens of computational codes which are free for academics. I think that GAMES is even free for commercial purposes. I'm not sure, that should be checked. But if you want to use for your own research within faculty, within university, you can freely use these tools. All of them are fantastic. There are these are just fragment of tools. I forgot here to place the Psi4 modeling program, and there is always a question whether to use commercial or free for academics. In my personal opinion, you should use whatever you can use, and it is always a wise thing to use more tools for computational modeling, because not every tool has everything. There isn't a computational modeling tool which contains all programs for calculation of all properties. You will always find yourself in a situation in which you have to use different tools for different properties. I am vastly using commercial solution called Schrödinger Material Science Suite. For my needs, it is the best possible tool. It is a commercial tool, but the possibilities which I have with that tool are fantastic, and I can investigate a lot of structures. For example, during a month, we can do a lot of work with that tool. But of course, there is a question of available financial resources, and that is why we need to fight for those research grants and stuff like that. So it is an open question, but please remember that I think, my opinion is that modern graphical user interfaces would allow you to cover more molecules, more crystals, and to do much more. I totally understand it is a question of financial resources. I would like to have more commercial solutions available in my laboratory, but unfortunately, the situation is as it is, so we have to fight for research grants. So as I said, these are just some of the free for academics tools, and let us now see what type of results, what we can actually calculate with, for example, density functional theory. Again, this is just a fragment what can be obtained with density functional theory calculations. I have chosen to deal with fullerenes because it is an interesting molecule for both physicists and chemists and for scientists coming from the technology area. And for example, you can obtain information about the charge distribution. When you know the charge distribution within your molecule, you can draw a lot of conclusions about its reactivity. You can check how the reactivity of that molecule changes with some modifications. So, for example, here we have the pure fullerene. My apologies. These molecule titles are not written in English. So here we have the pure fullerene, unmodified C60 molecule, the famous one, and we can see how the molecular electrostatic potential changes once we attach hydroxyl groups, OH groups, to the surface of the fullerenol. On the surface of fullerene, this is the so-called fullerenol. It has 24 OH groups, and we can see that the reactivity of such system tremendously changes after the modification in comparison with the pure fullerene. And this is the molecular electrostatic potential, very frequently, a quantity which is very frequently calculated in published papers. And this is the average local ionization energy, the ALI parameter, the so-called ALI parameter. And we can see that ALI also changes tremendously with the with the attachment of OH groups to the pure fullerene. Just a little introduction. This is one of the papers we published in Physical Chemistry, Chemical Physics journal some 3-4 years ago. So the challenge with fullerene is how to improve its solubility, and one of the ways is to attach OH groups, and we proved later in our molecular dynamic simulations that interaction with water tremendously increases, and increase of solubility and increase of interaction with water of fullerene contributes to the development of new drugs based on fullerene. So this is something what you can do. This is the paper which I found by some other researchers, and this is an example how we can, for example, investigate structural properties of fullerene-like cages. We can see how the structure changes when we change one carbon atom with, for example, cerium, nickel or titanium. And we can, for example, see, we can calculate the dipole moment, and dipole moment is a quantity which is connected to the charge polarization within molecules. So we can see that the highest charge polarization is introduced in C20 cage if one carbon atom is replaced with titanium atom, and you can find the results of this paper. You can find the results of this research in this paper. It is published in Materials Research Bulletin in 2018. This is just one example what can be done with DFT calculations. And then we arrive to the interaction, for example, of fullerenes with drug molecules. So cage molecules such as fullerene can be applied as drug carriers, and in order to act as drug carriers, they have to bind the drug molecule. And for example, you can calculate in a very nice manner the binding energy between some structure and drug molecule. In this case, as I said, I picked fullerenes because they are interesting for both physicists and chemists. And we can see that in this study published in Journal of Molecular Graphics and Modeling in 2017, researchers have calculated the binding energies between C60 fullerene and these drug molecules, and you can see which molecule binds the most and with the most strength to the C60. This is very important for the area of pharmaceutical science, for example, because in the pharmaceutical science area there is a branch dealing with the design and development of drug carriers, and calculation of binding energies is a prerequisite for those research. And nothing stops you to model this system on your own computers in laboratories in GLA University. Of course, this is a rather large system. It would take some time to geometrically optimize it, to identify the true ground state and stuff like that, because this system contains almost 100 atoms. But you can obtain these results and you can compare the binding energy, and we can see that this molecule, BCNU, the so-called carmustine, binds with the lowest magnitude. The binding energy has the lowest magnitude in case of this, and so we can conclude that the weakest bond is precisely in this case. So it is more likely that C60 can act as a drug carrier for these three drug molecules, TMZ, PCZ, and CCNU. And then again, when we talk about interaction between molecules, there are actually countless possibilities to perform research with DFT calculations and computation modeling. Here we have investigated, not we actually, some other researchers investigated the interaction of B40 cages with selected molecules, and I will stick to the hydrogen molecule, because why is important to investigate the hydrogen absorption? Well, because hydrogen is a fuel of a future. It is very important to find ways how to storage it, as it can be used as a fuel. So researchers worldwide are devoted to this design and development of new materials which can be used as a hydrogen storage materials, and it is important to obtain not too strong binding energies, because if you want to practically apply this material as an absorber of as a carrier, as a storage of for the storage of hydrogen, the binding energies shouldn't be too strong, because in that case, the desorption under reasonable conditions wouldn't be possible. So those are just some of the examples how these DFT calculations can be used. So there was one question, very interesting. What is the how does compare geometrical optimizations with or calculations with Avogadro and DFT calculations? As I said before, you are very limited with respect to the calculations when it comes to the application of Avogadro, but here we are going to see how much time does it take to calculate the how much time does it take to calculate to geometrically optimize propranolol with density functional theory calculations. So this is not the PM6. This slide should be first. No, this is a small mistake, and it is very reasonable. Very important mistake. It cannot stay in that way. Sorry. So these are the timings. These are the timings which are necessary for geometrical optimization of propranolol. So this is at the quantum mechanical level. I apologize deeply for this, but this is very important. I cannot leave it this way. So these are the timings that are necessary to geometrically optimize at quantum mechanical level of the molecule called propranolol. This is a frequently used beta blocker used for the regulation of blood pressure. It has around 40 atoms. And these are the timings for some of my old computers. So it took, on that same computer, it took a few hours to geometrically optimize this, this structure. Regarding the C60, which has, of course, 60 C atoms, on that older computer, it took 24 hours to geometrically optimize this molecule. It took 36 hours to optimize C70, 70 atoms, and it took more than 48 hours to optimize this molecule, which is very important for the solar cells. And this took even more, as of course, as the size of the molecule increases, the time necessary to geometrically optimize it increases as well. And of course, on that old computer, it was impossible to perform geometrical optimization on this large structure, not to mention this. So this was performed using the quantum mechanical level of theory. Please pay attention to the timings necessary to perform the task. But if we use the PM6 method, which is a semi-empiric level of theory, which is semi-empiric level of theory. I apologize deeply for this. Pay attention to the timings. Propranolol was optimized within few seconds, 40 atoms. C60 was optimized in less than half a minute. It took only 32 seconds to geometrically optimize C70. It took still less than a minute to optimize these two molecules. Remember, more than 40 hours was necessary to geometrically optimize this using the quantum mechanical level theory, using the DFT approach. And it was possible to geometrically optimize the C24. It took 5 minutes and 50 seconds. And it took 3 hours to geometrically optimize this system because it has a lot of rotable bonds. So we can see that if we apply semi-empiric methods, we can geometrically optimize even the large structures. So what I want to make a point here, and that is that on some stronger computer, this can be geometrically optimized on quantum mechanical level of theory as well, without some serious problems. And of course, the geometry obtained by DFT approach will definitely be more accurate than semi-empiric method. But the semi-empiric method in case of organic molecules and nanostructures will provide very similar geometries. So remember what I said. It is very wise. It is very wise to learn how to combine levels of theory because that can save you a lot of time. I made a table, and you can see that for C60 it took 24 hours on quantum mechanical level of theory, but it took only 26 seconds to optimize it on PM6 method. Of course, on some larger computer, on some more powerful computer, this can be done in even shorter time. And this is very important because on that old computer I was using, it was impossible to geometrically optimize C24, and it took only 5 minutes to optimize it with PM6 method. So what about really large molecules such as proteins? Here on the left, I have an example of C24 cage, and it is something that is possible to geometrically optimize using quantum mechanical levels, even either using pure quantum mechanical level or by using semi-empirical level theory. But there is no semi-empirical level of theory which can deal with the structure of protein. This is the 1WKR protein. It contains 2,520 atoms, and it is a really large structure for computational modeling at quantum mechanical levels. This is not a large protein, this is rather small protein. If you speak with a biologist and biochemist, he or she will tell you that this is not particularly large molecule, it is actually a rather small molecule. But for quantum mechanical levels of theory, it is impossible to perform calculations. It is impossible to perform quantum mechanical calculations, for example, geometrical optimizations on this large structure. So in this case, we're not going to use semi-empiric levels of theory, we're going to use molecular mechanics and molecular dynamics. And I just wanted to emphasize the fact that you have to carefully choose the level of theory for your system of interest. But there is always a trial and error approach. Of course, you can try to geometrically optimize this with quantum mechanical level of theory. The code won't even start because most of the codes are limited by the number of basis set functions which can be dealt with. So it would require an enormous amount of time to deal with this on quantum mechanical level of theory. But what I want to say is that remember that a fragment of this molecule can be treated with semi-empiric level of theory, while the other fragment of this protein can be calculated with semi-empiric level of theory, and there are some codes, molecular modeling codes, which can in which this approach can be applied. Some examples of what can be obtained with molecular dynamic simulations. I mentioned the importance to improve the solubility of fullerene, and here we have the so-called radial distribution functions, and here we have radial distribution function. The sharper the peak is, and the higher the G of R value is, it means that it is a higher possibility to find water molecule at that distance. We can see that the distance between the water and the OH group is very small in comparison to the distance between water molecule and pure fullerene, and this G of R value is much higher in case of fullerenol, and this is how we proved the distance is much shorter, and thanks to this much shorter distance, we proved that the interaction of fullerenol with water molecules is much more intensive, much more intensive. And of course, we investigated the influence of temperature. It is seen that the interaction is reduced on higher temperatures, which was in accordance with experiment, and this was very important result. So far, we have dealt, and I have presented only the molecules, but the same approach can be used for periodic structures or crystals. And as a physicist, I am somehow more related to crystals, but thanks to the collaboration with colleagues from chemistry department, I have still dealt more with molecules. So, but the bottom line is that there are modeling codes for the investigation of electronic structure of crystals. So the principles are same. Of course, technically it requires different tools to implement the DFT procedure for crystals, but the fundamental components are the same. And now I'm presenting you the structure of the periodic structure called zinc ferrite, and this is a magnetic structure. It has magnetic substructure, which I have been investigating. So far, we have published these results in Journal of Alloys and Compounds in 2020. And so what can we investigate by applying DFT calculations in case of crystals? Well, as you can see, we can investigate structural properties and the agreement between structure obtained through DFT calculations, and by experiments were in very good agreement. They almost matched. You can calculate what is known as band structure. So you can obtain information on the band gap. Band gap is very important, especially for solar cells or for catalytic properties. One of the attendants mentioned the catalytic, the area of catalysis. I'm using this opportunity to mention that Sanya and Maria from the chemistry department, also from the board of AIDASCO, they are working with photocatalysis of drug molecules, and they are applying nanomaterials to photocatalytically degrade these drug molecules. And it is very important to know the band gap of a structure, because if you can somehow manipulate the band gap, then you can improve the efficiency of a catalyst. You can, for example, narrow the band gap, or you can spread the band gap depending on what you want to achieve. And as scientists dealing with catalysis know very well, by finely tuning the band gap, you can use the light in a more efficient manner. That is what scientists dealing with photocatalysis know very well. And you can, of course, obtain information about density of states. You can see how each and every atom or impurity or dopant contribute to the density of states, which is very important to understand how your modifications are changing the electronic structure of your crystal of interest. Although somebody would think that crystals are easier to be dealt with because they are periodic, it is not the case. In my personal experience, it is a little bit, for me actually, it is a little bit a little more difficult to deal with periodic structures, because in some way molecules are more intuitive, but and from the technical aspect, it is a little bit easier to implement the DFT code for isolated structures or molecules. But let me mention also that developing a modeling code is very difficult. All of these codes, either for dealing with molecules or structures, they are having hundreds of thousands of lines of code. It is always a result of collaboration between hundreds of people. It is impossible that only one person writes the modeling code completely alone. It is practically impossible. So you can investigate crystals with DFT. You can investigate combination of periodic structures and molecules. For example, if you want to investigate transport properties, you can use DFT or DFTB level of theory. And this is the example of DTO-benzene molecule between the two gold electrodes, and there is the so-called NIGF approach to calculate the IV curve and to obtain information about the differential conductivity of molecules. So this molecule and this setup is something that has been achieved both experimentally, and theoretically. This is the most frequently studied molecule between electrodes, because it has some good characteristic and is suitable for investigation of electron transport. And this is very important because experimentally you are limited which molecules you can place here, but theoretically nothing prevents you to place here whatever molecule you want to have here, and to calculate its IV curve, or to obtain information about differential conductivity. These results are obtained with commercial code, which is very powerful, and it is called the quantum ATK. Now that code is part of the synopsis, but it was originally developed by QuantumWise. So we talked about molecules, periodic structures. We have mentioned different levels of theory, and that brings us to the so-called molecular docking. And what molecular docking is essentially, you investigate possible orientations and binding sites between ligand and protein. So it would be very difficult and time-consuming to minimize and to optimize the geometry of a system containing both protein and ligand. But what you can do is you can identify possible sites on the protein where ligand could possibly bind, and then you can check how different conformations of that ligand would bind at that particular place in protein, and then you can use something what is called scoring function to classify the best docking modes. So how this works in practical manner? Well, you download the crystal structure of a desired protein from the PDB, Protein Data Bank. Remember what I said and when I mentioned that, for example, the COVID-19 protein is available for more than a year there. So you download that crystal structure of a protein. There are some steps that you have to perform in order to make it suitable for calculation. And then you define the binding site, which most frequently has been known through experimentation. And then you try to bind your own molecules and see through the scoring function how different molecules behave on that binding spot. So some molecules and some of their conformations will have the high scoring function, and some of them will be having a low scoring function. If the scoring function, of course, is high, that means that that ligand, that drug molecule, is tightly binding to the protein, and if it is low scoring, or if the scoring function is low, then it means that it binds weakly. Of course, sometimes for some proteins it is necessary to bind strong, and some proteins require weaker bonding. That is very complex area, of course. You can define the binding site, or you can consider the whole protein. When you consider the whole protein, then that is called the blind docking. So usually you have some experimental data indicating which part of the protein are likely to be binding spots. But if you don't have those information, then you have to perform what is known as blind docking. The whole protein is a possible binding site. So, of course, those calculations are a little bit longer, but the docking is very quick procedure. Actually, the calculation itself is relatively quick. The preparation of ligands and proteins is something that, after some time, doesn't require too much time. And there are procedures, there are tools, computational tools, which automate the whole procedure, so you can investigate really a large number of proteins and possible drug candidates. And last but not least, I would like to mention the drug likeness parameters. Thanks to the development of various levels of theory for computational modeling of particularly molecules, at one point in time, scientists realized that they can calculate a set of quantities for molecules which are known to have good pharmaceutical, physical, and chemical properties. So what they did, they calculate the so-called drug likeness parameters for molecules which are on the market, which are having good properties. And in that way, they obtained critical values. They obtained information about critical values of some of the drug likeness parameters. And drug likeness parameters are quantities which indicate whether some molecule could possess suitable physical properties to be applied in drug formulation. So, after realizing what are the critical values, you can calculate for your own new molecule. For example, if you can synthesize some new molecule in your own laboratory, you can check whether that molecule has potential to be applied as a drug or not. So if it has a suitable values of drug likeness parameters, then it is more likely for that molecule to have suitable physical properties to be applied in drug formulation. And let me just mention here, this is also a complex area, but biological activity is not the only thing that it is required for active substances in drug formulations. It is also necessary that those active components have suitable physical properties, so they can be absorbed, so they can travel through organism, through body, and to deliver the biological effect. So to check if that molecule of yours has suitable physical properties, you calculate the drug likeness parameters, and if those drug likeness parameters have suitable values, then you can make a conclusion whether it is going to be, whether it might have good or bad physical properties for drug delivery. So the best known example of application of drug likeness parameters is the so-called Lipinski rule of 5, and Lipinski, if I'm not wrong, Lipinski defined this law, this rule, while he was working for Pfizer, and it is also in the literature known as a Pfizer rule of 5 sometimes, but most frequently it is known under the name of Lipinski rule of 5. So if your new molecule has log p values lower than 5, if it has number of donors of H bond lower than 5, number of acceptors of H bond lower than 10, molecular mass less than 500 daltons, and molecular refractivity between 40 and 130, and polar surface less than 140 squared angstroms, then it is very likely that your molecule is going to have good physical properties. In other words, it is more likely that your molecule could travel through the organism and deliver the biological effect. Why is this important? Well, this is important because it allows us to identify the best candidates for development of new drug formulation. So in our laboratories, and experimentalists know that very good, in our laboratories we are able to synthesize a bunch of molecules. We can attach different chemical groups to our molecules. We can have hundreds of molecules, thousands of molecules, and tens of thousands of molecules. So what is the problem? If we have 10,000 molecules, we theoretically cannot investigate them, all of them experimentally. We cannot check pharmaceutical properties of all of them. And that is very large problem. We have to somehow narrow the number of these properties, number of these molecules, and from these molecules, for example, if we have 10,000 molecules, we have to somehow choose the best candidates for drug formulation. And that is where we apply computational modeling. Firstly, we start with drug likeness parameters, or we start with molecular dynamics to see whether which of these molecules can attach to some or can interact with some of the proteins which are relevant for us. Then we check whether which of these molecules have suitable drug likeness parameters, and then we select the best candidates for experimental investigation, because, as I said, it is impossible to experimentally investigate all of the starting molecules. We have to filter the selection. In the end, we have to make the selection, and we always experimentally investigate only the best candidates. So this is the way how new drugs are developed. It takes a lot of time. It takes a tremendous amount of financial resources to make a new drug and to place it on the market. And first steps are computational modeling techniques. So we investigate, actually scientists working in pharmaceutical industry, they firstly investigate reactive properties of molecules. They use quantum mechanical calculations to check if their molecules are going to be stable. Of course, you can check to what extent your molecules is stable through experimentations, but that is expensive. It takes time, it takes a lot of financial resources, so it is much better to first computationally investigate that, choose the best candidates, and that is how the pharmaceutical industry is working. They are using molecular dynamics for the development of molecular dynamics in combination with drug likeness parameters and quantum mechanical calculations to develop new drugs. So this is essentially everything that I wanted to mention today, and I would be, in a way, we connected second and the third session. So as far as I'm concerned, this is everything that I wanted to say today. Before we start with the questions, I would like to ask you to visit all of these links and to follow the AIDASCO impact factors online on social networks. It would really help us to promote all of these services, and especially of course AIDASCO.
Thank you, Dr. Armaković. Now I will request the audience to please ask the query if they have any.
Dr. Stevan, am I audible?
Yes, yes.
Yeah, actually I have a query to ask.
Sorry. I have to interrupt because there is a microphonic effect. If somebody could turn off just please the speakers.
Okay, sir, just wait a second.
Oh yeah, now it's okay.
Am I audible now?
Yes.
My query was, is it justified to compare the free energy charge of two reactions and which one is favorable?
I am really sorry, but somebody should have to mute the speakers, or I think that you should mute the speakers because I don't understand you. Can you please write the question?
Okay, I'm right.
Dear Anas, okay, you can drop your query, okay, in chat box.
Okay, sir.
And Aditi ma'am, you please mute yourself.
I apologize for this, but I wasn't able to hear the question.
Anas, please
Yes.
Please mute yourself first.
Okay, sir.
Oh, sorry. Okay, so is it justified to compare the free energy charge of two reactions? Well, to be honest, the free energy, do you think in terms of quantum mechanical calculations or in terms of molecular dynamics? But it is definitely justified to compare the free energy of reactions, because that is what has been done to to check which channel of reaction is more likely to be performed. But for these purposes, to investigate the chemical reactions, it is firstly necessary, and the most challenging task in investigation of reactions is to identify the transition state. So what is the transition state? Well, that is the transition between, it is a specific transition, it is a specific state between the starting and the ending products, and starting and the ending geometries of reactants. So there is no when students or young researchers, when they ask how to identify the transition state, how to search for a transition state, there is no straight answer. And usually the tutorials and manuals and books say you have to follow your chemical intuition, where it is going to be, where the reaction is going to happen. But that is the moment where quantum molecular descriptors help us to identify where might the transition state occur and what might the transition state be. And let me also mention that there are tools with automated transition state search possibilities, for example, like in GLA program of Schrödinger material science. So yes, your question is very good. It is justified to, in my opinion, free energies are also important parameters for the investigation of reaction channels. But to be honest, reaction channels, investigation of reaction channels are not something that I'm mainly dealing with. I'm mainly dealing with material science in terms of absorption, in terms of electronic structure. And this is certainly definitely interesting question. We can later maybe do a literature check and provide maybe more detailed answer. So the second question is how to do best model adsorption onto quantum dots with density functional theory. That is something that is very frequently performed with the DFT calculations. So there is a question how to model quantum dots. So usually there are some papers, for example, where quantum dots, where graphene flakes have been considered as quantum dots. When you say quantum dots, you think on in terms of computational modeling, you think on isolated molecules. And how to do that in the best manner? Well, the best way to do that is to apply the suitable functional, if you want to choose DFT calculations. And the suitable functional for that is not the B3LYP, the most frequently used functional. So in this case, it should, firstly, you should perform your calculations with B3LYP D3. I'm going to write that level of theory. D3, level of theory. So this is the level of theory which you should perform initially for investigation of adsorption. So why? Because the pure B3LYP is not able to treat dispersive forces in an adequate manner. So you have to use the dispersion corrected variant of B3LYP. So this is the empirically corrected. B3LYP D3 is empirically corrected level of theory. Which means that empirical approximations have been used in order to modify the equation which according to which the energy is calculated. And this D3 part is obtained thanks to the work of the famous Stefan Grimme from Germany, famous physical chemist. He introduced this empirical dispersion correction to B3LYP, and you have D3 addition, let's call it like that, you have D3 correction defined for practically all of the relevant functionals. So for example, you have the PBE D3, you have, for example, the MO6 to X D3 correction. So you have D3 correction for for all relevant functionals. And lately there has been introduced the new generation of dispersion correction. So probably there is going to be D4 or something like that. Not DE, but D3. I apologize for this. D3. There is one more very important answer to this question is why it is advised to use B3 LYP D3, this empirically corrected dispersion, because this level of theory, I hope you see now it marked, this level of theory is just slightly more computationally expensive than the pure B3 LYP. So for your initial calculations on adsorption, I strongly recommend to use this, and then to use this. Then to use this, MO6 to X. So this is the member of Minnesota family of functionals, and this functional, MO6 to X, has been particularly defined to treat dispersive forces. And how they did it, they introduced a lot of adjustments into that equation. They parametrized a lot of quantities, and that is the main reason why MO62X is much more computationally expensive than B3 LYP D3. And of course, so this is empirically corrected, and this is specially designed functional for DFT calculations for calculation of binding energies. Because whenever you have non-covalent interactions, you should avoid B3 LYP and use B3 LYP D3 or MO62X. Now let me mention one more very important thing, and that is that so far you have improved versions of Minnesota family of functionals. I think that right now you have MO8, you have variants different, and but not all, but older programs, older versions of programs don't have the latest, unfortunately, the latest family of functionals. Why am I mentioning this? Well, because, for example, the Gaussian, the most popular version of Gaussian is Gaussian 09, and a lot of researchers from India are still using Gaussian 9 version of a program. And, for example, you don't have the latest functionals there because it is a 10 years old software. Of course, yeah, everything is a matter of possibilities, and you know, everything, research is expensive, but there are some other functionals in those versions of programs which are suitable for investigation of adsorption through this. So whenever you have adsorption and whenever you have non-covalent interactions, you have to carefully pick the level of theory, and that by that I mean if you want to use DFT calculations, you have to. It is my suggestion to use this or this. Of course, it would be also reasonable to use this dispersion corrected MO62X. Of course, what is very good is that scientists who develop new functionals, they publish papers about that, so it is very good suggestion to read all of those papers, and to then they report how their functionals perform on a set of molecules. There are certain standard sets of molecules which are used for performance checks of new functionals, and then you can see what they report. Let me also mention that there are dozens, hundreds of functionals developed, and there are hundreds of papers where performance of new functionals is compared. So it is really a sea of functionals. It is an ocean of possibilities. But these are some standard suggestions for beginners.
thank you so much, Dr. Armaković, for this knowledgeable session delivered by you, in which you have covered overview of methods for computational modelings of molecules and periodic structures. The whole session was very knowledgeable, and I also have learned very new things here, especially the fluorine, the use of that. It was always very nice. So now, on behalf of IQAC Research and Development Cell, GLA University, Mathura, India, I am very much thankful to Dr. Armaković for his acceptance and sparing time to make this audience aware about how to structure a good research paper, an introduction to computational modeling of molecules and periodic structures. I hope with what advancement you make the scholars aware, they will definitely use in their upcoming research work, and also thankful to all my faculty colleagues and scholars for joining and making this talk successful. Before ending this, I have just seen that there's one more query of Ms. Saloni Bansal.
Yes, yes.
So we should take that also.
Yes,
so what
of course.
are the models used for quantum dots in Silvaco TC82?
I'm not familiar with Silvaco TC82. You didn't even hear for this. I presume that this CAD means computer-aided design, and this is something new for me. I'll have to read about it.
Okay. So once again, I'm thankful to IQAC Research and Development Cell, GLA, Mathura, India, to provide me the opportunity to jointly conduct this expert talk. Thank you, Mr. Armaković, and
thank you very much. I would also like to mention that this was a great honor to participate in these events. If you have any questions, please feel free to contact me or other members of AIDASCO. Please visit the websites I mentioned. It would mean a lot to us to follow those to follow us on social networks. In that way, you would help us to promote our causes and goals. And feel free to contact us, and also medias in Serbia from time to time report on the situation in India regarding the COVID pandemics and outbreak. We all pray for our dear friends and colleagues from India that this situation will soon improve, and we all hope for future collaboration.
So thanks a lot, Dr. Stevan, for sharing your erudite through this invited expert talk, and looking forward for further collaborative work together.
Thank you very much.
Thank you. You please take care.
Yes, thank you very much. You too.
See you all once again in near future. Be safe. And so with these words, now I think we should end our meeting. Thank you, each and everyone. Thank you.
Thank you very much. Bye. Stay safe.
Bye.
Bye, Dr. Stevan.
Thank you.